Morning, good afternoon, good evening, good night, wherever you are watching this. Hopefully, this video finds you well and not panicking too hard. But today we're going to be talking about formal charge. Now, formal charge is something that I am super passionate about when it comes to teaching because, well, I'm sure as Dr. Koh and all of his TAs and almost any other chemistry teacher on campus can attest to, is that formal charge is something that is pretty simple in theory, but when you're in the heat of organic chemistry and you're trying to do reactions at a million miles an hour and try to beat the clock on an exam time, what's going to happen is that eventually you might forget the charge of certain things. And essentially, that's what formal charge is. That's all it is, the charge of certain atoms given certain conditions, whatever they're bonded to, if they're undergoing a proton transfer, some sort of reaction, eventually you'll change. Normally, atoms like to stay neutrally charged, but sometimes through whatever circumstance, they can be negatively charged. They can have -1 plus -2 charge, +1 +2 charge, depends on the context. But formal charge is very important because if you forget to do it and you forget to account for it, you will go through something, both you and your grade will go through something called what I like to call death by 1,000 cuts. You'll end up seeing on your exam -1, -0.5, -0.5, -0.5. And when every single point counts, you really, really, really cannot be messing up charges. So we're going to do our best today to make sure that that does not happen. I'm going to make sure that you guys will have the skills needed to ensure that you do not die painful death by 1,000 cuts. So, with that being said, every single conversation about formal charge always starts with the idea of valence electrons. And I will warn you guys, I'm going to be skipping over some very, very, how would you say, hard theory. I teach operationally, which means that I teach you what you need to know during this class. That's all. When it comes to actual theory and whether or not things are true or not, or how much nuance it is, you can go talk to Dr. Koh about that. But I don't have a PhD, obviously. But essentially, all you want to know is valence electrons. If you don't know, valence electrons are essentially the electrons that are in the outermost shell of an atom. And so I'm sure all of you here have seen I believe it was called the Bohr model. I'm pretty sure. I could not be bothered to check, but you guys have seen this model before, right? Where you have a nucleus in the middle, right? This little black ball right there that has the protons and the nucleus, the protons and the neutrons. And you see concentric rings, and each ring is kind of lined with electrons, right? But on the outermost ring, I'll highlight these in red. On the outermost ring here, these electrons are called valence electrons. I'll highlight this in red for you to figure it out. Yes. These ones are called valence electrons. So these electrons are going to be the ones that are responsible for essentially bumping into other atoms and forming bonds. I'm sure, as all of you know already, bonds are basically made of atoms coming together, electrons of atoms coming together and holding hands, hugging, whatever, and essentially forming a bond there. And the atoms will then share those two electrons. So these electrons are going to be the ones that are responsible for formal charge. And so when it comes to valence electrons, knowing how many valence electrons is going to be key in 99.9% of scenarios to figuring out how many bonds a certain atom will have, and therefore what charge it will be in certain conditions. Starting off with the most important element that you'll encounter, it's carbon. Carbon has 4 valence electrons. And the neat thing about chemistry and the way the periodic table is set up as a whole is that once you know the valence electron count for one atom, every single atom that is going to be in that column is going to be the same one, same valence electron count. So carbon will have 4, silicon will also have 4, germanium will also have 4, so on and so forth. And equally easier for everyone to remember, right? Nitrogen has 5 valence electrons, oxygen has 6 valence electrons, fluorine has 7. 4, 5, 6, 7. All of us hopefully know how to count, and that should be easy for us. And therefore, that means that for nitrogen, right, you got 5 here. That means phosphorus also has 5. Arsenic also has 5. And on top of that, too, oxygen has 6. Therefore, sulfur has 6. Selenium has 6. You get the point. Yeah? So how exactly would we use this in organic chemistry 8B? Like I said before, double disclaimer, this isn't going to be an explanation 110% behind the theory of why things happen a certain way, but this is going to be just going to be teaching you how exactly to use formal charge to ensure that you don't die of death by 1,000 cuts. And as you do organic chemistry and you practice your reactions, which you should be doing when we get into that phase, things will get easier, I promise you. So let's first start off with this example over here, CH4. methane molecule. So the way that I would determine the formal charge of this is first I had to figure out, okay, what atom are we trying to analyze here? So carbon, right, is what we're trying to look at. So carbon, as we established earlier, has a valence electron count of 4. So I would write that down really quickly, 4. Then from here, I'll count how many lone pairs and how many bonds there are attached to carbon. Yeah. So I count 1, 2, 3, 4. And therefore, I'll take that number, subtract it from our original number, and there we have 0, which means that this carbon right here, this overall molecule will have a charge of 0, which means that it's neutral. I'll give you a second to pause and think about that. But that's basically the gist of it. This is probably going to cover maybe 60% of scenarios, I would say. Now, for this oxygen over here, yeah, moving on to this next example, we will count the bonds like normal. However, the lone pairs, right, you count the electrons individually. So we go back to the periodic table. Our table, oxygen has 6 valence electrons, so I'll write down 6. And then I'll count how many bonds there are and how many individual electrons there are in lone pairs. So I'll count 1, 2, 3, 4, 5, 6. 6 minus 6, once again, is 0. This oxygen will have a neutral charge. I will move on down here to sulfur, right here. We go back over to this right here. Sulfur also, conveniently, since it's in the same column, 6 valence electrons. And I'm sure you guys could probably just close your eyes and just do this by now, yeah? But I will go ahead and I will count the amount of individual lone electrons and lone pairs there are, and the bonds. I count 1, 2. Sometimes you'll see this being drawn here. Not every bond has to be shown, but there's a bond there between S and H. So 1, 2, 3, 4, 5, 6. And I want you to look at that. 6 minus 6 equals 0. Okay, let's move on to this nitrogen over here. Nitrogen, how many valence electrons are there? 5. Okay, cool. So we'll start off with 5. Minus, let's count. 1, 2, 3, 4, 5. 0. How lucky we are. Look at that. We have basically 0 formal charge all around. Now, things do get a little tricky when you start actually having to do the reaction to do certain things. Okay, cool. Let's do an interesting example here, right? So let's have a water molecule. Big fan of water. Can't go 3 days without it. Tastes great. So let's first figure out what the formal charge is of this oxygen just by default. So we go back to the table. Oxygen has 6 valence electrons. Yeah. So 6, and let's count. 1, 2, 3, 4, 5, 6. 6 minus 6 equals 0. How beautiful. Let's say, for example, this H2O is just floating around in a cup somewhere, or I don't know, in a tire after it rains. And all of a sudden, right, it encounters another water molecule. And through some fun little happenstance, right, what happens is that this guy over here is going to go and steal this H right here. Right, it's going to do a quick proton transfer. And if anything right over here confuses you, right, I will probably link a video to the acid and base stuff and the arrow pushing stuff. But let's say the proton transfer happens, right? And now we have an extra H on here. I'll go ahead, you know what? Give me 1 second. Let me just reform this to make sure that it makes sense to you so that nobody's lost. Let's make this in green. Big fan of the color green. God, I hope none of you are colorblind. Yes. So we now have this guy right here. He's basically attached to it. Okay, now so the count of valence electrons and lone pairs. I believe the count of bonds and the count of the lone pairs has changed. So let's go ahead and let's analyze this. So originally, right, for this oxygen, we started off with 6. Now let's count the amount of things attached to it. 1, 2, 3, 4, 5. Interesting. 6 minus 5 equals +1, +1. Therefore, this oxygen is going to have a positive charge. This H3O is going to have a positive charge. And you often see this around. This is hydronium. Yeah. H3O plus. Okay. Hopefully that was easy to wrap your head around. So this may seem easy right now, but like I said before, when you're in the heat of doing chemistry, you're rushing through reactions to finish in the last 10 minutes of a test. Sometimes it can be difficult for somebody to keep track of all of these. And honestly, the best way to do this is to practice over and over again. If you ask me while I'm in my sessions about what we should do about formal charge, just practice. That's literally the answer to 99% of your problems. But let's go over another example. Yeah, let's say, for example, right, you have HBr. Actually, you know what? No. That's not my favorite acid. I'm a big fan of, I'm a big hydrochloric acid fan. Big stan hydrochloric acid, yeah. So first and foremost, right? Let me go ahead and quickly just draw in these lone pairs here, right? Let's figure out the default charge of this chlorine atom right here. So let's go all the way up through here, right? So chlorine is the same column as fluorine, which means it has 7 valence electrons. So coming down here, we'll start off at 7. And let's count. 1, 2, 3, 4, 5, 6, 7. Okay, easy enough. 7 minus 7 equals 0. So no charge just yet. However, let's say you encounter a wild base, an AOH. Yeah. And let's say this base over here, right, goes in, attacks this H, this pops off, right? Does a quick proton transfer. And if you're confused, we'll talk about this in a second. Yeah. So now have this thing. You have this chlorine kind of floating around because that NaOH over there just stole that H. And so what's going to happen here, right? Obviously, the charge has probably changed. So it's still the same chlorine. So we start off at 7. Now let's count. 1, 2, 3, 4, 5, 6, 7, 8. 7 minus 8 is -1. Therefore, this chlorine anion will have a negative charge around it. This is basically the gist of everything. Like I said before, this is pretty easy, I would say. Hopefully it is. The logic isn't that bad. However, like I said before, practice, and sometimes when you're in the heat of things, you tend to forget things. Okay? So let's go over some of the minor examples, or I want to say minor examples, right? Let's go over an example that's kind of a bit of an exception to a lot of these, this pretty simple electron counting method that I just shown you. And so we established earlier, right, that, let's say, for example, oxygen could have 6 valence electrons. Let's say, for example, you're chilling with one of your friends. So, I don't know, you're taking a break from studying. And your friend asks you, okay, so oxygen has 6 valence electrons, right? Could I hypothetically do this? If you guys can't tell, that's an oxygen with like a bunch of like different things attached to it. This looks kind of like a sun, spider, whatever. And your friend argues that, okay, this should be legal, right? This is something that I can do because oxygen starts off with 6, right? And we count 1, 2, 3, 4, 5, 6. Is that mean that this oxygen over here is 0? Like its charge is 0? Is this even possible? Is this plausible? Now, you might be thinking, right, if you were just recently introduced to this rule, you may be thinking to yourself, well, yeah, I mean, by what, Ryan Lowe just taught us, yeah, that makes sense, but this looks kind of funky. It's just a little weird, right? Well, there's actually a rule that you also have to keep track of as well when you're doing charges, right? If you do chemistry and you end up violating this rule, it means you've done something wrong. And that rule, it's very important. So I'll highlight it over here. It's called the octet rule. Now, like I said before, I'm not going to go into all of the nitty-gritty theory behind it, but essentially, right, octet rule is basically just another layer of things that you have to check to ensure that whatever you're doing isn't violating like any interactions with valence electrons. So this is a bit of an extreme example, but essentially, right, to check if something has violated the octet rule, essentially you have to count every single bond around it, all the electrons that are in the bonds around an atom. And so instead of counting just 1, yeah, like I did here, 1, 2, 3, 4, 5, 6, essentially I'm going to count, I'll do this in a different color. I'll do this in purple, right? I'm going to count 2 for each one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And when you do this octet rule counting, the number should not exceed 8, as implied in the number octet. And as I just counted, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, this definitely violates the octet rule. So this is illegal. No spider oxygens. Now, in a less extreme example, right? Let's go back to good old friend carbonyl over here, right? Let's check to see if what we did here basically violated the octet rule or not. So what we have here, right, is an oxygen. And as we said before, we'll just quickly do this count, right? So there's 6, right? Because oxygen has a valence electron of 6. And minus 6 things to count to. 1, 2, 3, 4, 5, 6. Yeah. And that should be okay. Yeah. So that should be 0. Now let's do the octet rule counting. Yeah. So we'll count 2 for each bond. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, and this purple over here is for these 2 lone pairs. So I count 8, counting the lone pairs individually, and then counting 2 for each bond, right? So it matches 8 exactly. That's exactly where we want to be. You need, like, whatever you do to an atom, it needs to match the octet rule counting. It needs to be able to equal exactly 8. So that's just an extra layer there. So let's do like a very interesting example here. Let's say, for example, right, let's do this nitrogen right here, right? Let's say this nitrogen did whatever proton transfer, and you end up with this. Yeah, we end up with an H here. All right, so first and foremost, let's quickly calculate this together. You can pause the video at any time if you want, so you can figure it out yourselves. Nitrogen has a default valence electron count of 5. And doing the count, 1, 2, 3, 4. Yeah. So 5 minus 4 equals +1. So this is going to have a plus charge. Now let's do the valence electron. Let's do the octet rule counting. 1, 2, 3, 4, 5, 6, 7, 8. Aha, it's 8 exactly. So it checks the octet rule. So this is legal. This is a legal structure you can draw. Yeah. Even though there's some changes in the formal charge, you still have to obey the octet 8. And so with that being said, that's basically it for this episode. Hopefully you guys are all doing well. Please study hard. And remember, go down fighting.